Hello everyone, welcome back again to C++ real-time audio programming with Bela. We've been working through a series of topics related to synths and audio effects and coupling those to topics in the C++ programming language. Today we're going to talk about a really fundamental issue in real-time signal processing, which is how to deal with time. Now this might seem like a very obvious thing to do, but it requires us to think about handling time in a slightly different way than we might be used to in other programming environments. In this lecture, we'll look at how to count audio samples as a way of measuring time. We'll see how to create delays and recurring events, and also how to generate signals over a particular interval. By the end of this lecture, you'll make an adjustable metronome with LED feedback. We'll also update the step sequencer example we saw in a previous lecture to make it automatically step through the sequence on a clock. As always, you can find companion materials, including code examples, at the GitHub link at the bottom of the screen. And of course, like always, you'll need a Bela starter kit or a Bela mini starter kit to follow along with these lectures. For this particular lecture, we'll also make use of a potentiometer and an LED, so you'll also need a breadboard and some jumper wires. However, you'll be able to complete most of the code in this lecture without any external hardware. The previous lecture in this series looked at how to implement digital filters in real time, and we saw that there were a number of different types of filters that are regularly used in audio. What they all had in common is that they were calculated as a weighted sum of the previous input and output samples. The weights were called the coefficients, and the values of those coefficients determined what kind of filter that we had. As we discussed last time, filters are typically linear time-invariant systems. What linearity means is that if we add two signals together and then filter their sum, that produces the same output as filtering each signal individually and then adding the outputs of the two filters. Time invariance means that if we shift our input signal in time, the output signal will shift a corresponding amount in time. In other words, the system is behaving the same way all the time. When we calculate a filter, time is an important quantity, but mainly in an implicit way, in the sense that we're using the previous inputs and outputs to calculate the current output. However, we'll also encounter a lot of situations where we need to explicitly deal with time in signal processing. For example, we might want to build a system which generates an output signal at a regular interval, say every n seconds. Other examples might be to wait a certain period of time and then generate a signal, to generate a signal that lasts a certain amount of time and then stop, or to measure the time difference between two events. All of these problems require that we explicitly take account of time in our signal processing. How do we do this? Let's start with one simple case where we want to wait for a period of time and then generate a signal. And let's say that it's 5 seconds that we want to wait. We could write some code that looks like this, where inside of our render function we call a delay function telling the code to wait for 5 seconds before generating the signal. The question is, does this work? Unfortunately not, and the question is why. To answer that, let's go back to the beginning of this lecture series where we talked about how we process real-time audio. As you may recall, we process audio in blocks of several samples, and we call a function like render each time we have a new block of audio to process. The block size could be quite large or quite small depending on the particulars of the system, but what every block-based system has in common is that we are always calculating one block while the audio hardware is playing the block we calculated right before, like this. Here's why that means that we can't call a function like delay. Our job in the render function is to calculate one block of audio and get out of the way as soon as possible so that the system can handle sending that block to the audio hardware. We have strict deadlines on when our render function needs to finish, and if we miss those deadlines, what we're going to get is not a delay, it'll be an underrun and dropped outputs. We also need to remember that in a real-time audio system, when we do the audio computations is not the same time that the signal plays back through the hardware. By the time our render function is called, any inputs that we are going to work with have already been captured, and similarly, any output signals we calculate won't actually appear on the hardware until the next block. This means we can't use when the computations are done as a reliable guide for measuring timing. So what should we do instead? What we want to do instead of a delay statement is to count the elapsed time as we go along. If you've used a platform like Arduino before, you might be familiar with a function called millis, which returns the number of milliseconds elapsed since the board powered up. We do have Linux system calls on the BeagleBone that can also give us the clock time, though there are a number of problems with this. First of all, it would give us the time of computation, not the signal time, and second of all, these functions tend to cause mode switches, where our Bela program drops its real-time priorities in order to access the Linux system, and this also degrades our performance. Okay, so what should we do? The best answer, typically, is to count the number of audio samples that have gone by. Recall that each real-time block is composed of a number of audio samples. We know how many samples there are in the block, and we also know the sample rate. Therefore, we can calculate the elapsed time in seconds as the number of elapsed audio samples times the sample rate. Aside from being simple to compute, this also has the advantage of telling us the time of any particular point in the signal, and not just the time that the computation took place. Therefore, if we want to schedule a future event, we need to know how many samples in the future it should take place. For example, in the case of a 44.1 kHz sample rate, how many samples would need to go by for a tenth of a second? The answer is that it's 0.1 times 44,100, or 4,410 samples. Now, it's very likely that many of these future events will actually happen in a future block. Therefore, we're likely to need to use global variables so that we remember what needs to happen in future calls of render. There's basically two approaches to using a global variable to keep track of the timing. The first approach starts the variable at a value of 0 and increments it each successive audio sample. Once it reaches the desired count, then we know that the right amount of time has gone by and we can do whatever it is that we want to do. The other equivalent approach is to start the variable with the desired delay time stored in it and decrement the variable every single sample until it reaches 0, and then at that point you can generate the event. This brings us to the first task of this lecture. In the companion materials, there's a project called Metronome. When completed, this example will play a regular click sound, as its name implies. What you need to do is implement the code inside of render and implement any needed global variables so that the click plays every half second. This example builds on a sound file player class, which we looked at in the previous lecture. Just know that to start the sound playing, you call gplayer.trigger. Take a moment now to see if you can make this code work. Pause the video here. Let's start by looking at the most critical code for the metronome. You can see that at the top of the file we declared two global variables. One holds an interval, which tells us how many samples should elapse between clicks, and the other one holds a count, which updates according to how many samples have elapsed so far. Inside of the render function we have our usual for loop, and inside of that we have this if statement. What the if statement is doing is it's incrementing gmetronome counter, and then it's checking if the count has reached the interval. If that's true, then we're going to do two things. First of all, we'll reset the counter to 0 so that the next time around we start counting all over again. And second of all, we'll start the click playing by calling gplayer.trigger. Below the if statement, we're always calling gplayer.process. We talked about the architecture of this class in the previous lecture, but the idea is that the process method is always called regardless of whether the sound file is playing or not, and we're going to use the trigger method to tell the sound to start playing. Here's an alternate version of the code that works the same way. In this case, we start the metronome counter equal to the interval, and we decrement the counter each time. When the counter reaches 0, then we reset it back to the interval and call trigger as we did before. For all practical purposes, these are totally equivalent approaches with identical performance on any modern compiler. I show you them both because you'll see both style variations. If you were working with very low-level code in assembly language, say, it's more common to use the second of these approaches, decrementing a counter and checking if it's equal to 0, because you can save yourself one comparison, but any modern compiler will optimize these both to be the same kind of code. There's one other approach you can use on Bela to do something like this, and that is, inside the Bela context, there is a variable called audio frames elapsed. Audio frames elapsed holds the cumulative number of samples from the beginning of the program to the beginning of this particular call of render. That quickly becomes a very big number, so audio frames elapsed is a 64-bit integer value. What that means is that it can hold numbers up to 2 to the power of 64, which, at 44,000 samples per second, works out to about 13 million years. So suffice to say, this counter is never going to be rolling over. However, if you were using only a 32-bit value, it would roll over every day or so, which could create glitches in your program. You can use audio frames elapsed to do something very similar to what we saw in the previous examples, but in practice the previous approaches are usually more common. That's because we're usually more interested in the relative time between two events than we are in the total amount of time since the program started running. Alright, let's turn our attention to the full code example then. Here we have the completed metronome project. We can see the two global variables declared at the top of the file. Notice that they're both set to 0 right now, including the interval. The reason for that is that I've calculated the metronome interval here inside of setup. I don't want to make any assumptions about what the audio sample rate might be, so I wait till it's passed in inside the Bela context, and then I store it in gmetronome interval here. Most of the action happens inside the render function. Here, we have the if statement that checks if our counter has exceeded the metronome interval. Notice that there's the plus at the beginning of G metronome counter. By putting the plus at the beginning, what that means is that we increment the counter first, and then we check if it's greater than the interval. If we put the plus at the end, then the comparison would happen first and the increment afterwards. This code we've already seen. We reset the counter to 0 and call the trigger method to start the click playing. And then here is our process function that gets the next available sample out of the audio buffer. So we can run this code and hear our metronome. All right, there we go. That's a good start then. We've seen that we can generate an event that happens every half a second. But of course, to make a practical metronome, we want to be able to adjust its tempo. Typically, when you look at a metronome, you don't see its tempo specified in hertz or in seconds. You see it in beats per minute. So we need to work out how to convert beats per minute into an interval in samples. So let's suppose that our tempo is x in beats per minute. First ask, how many minutes per beat is that? Well, that basically is just turning it around. So we have x beats per minute is 1 over x minutes per beat. Okay, well, how many seconds per beat? Well, 60 seconds in a minute, so we have 60 divided by x seconds per beat. Finally then, how many samples are there per beat? Well, here we need to refer to the audio sample rate, and we get 60 times fs divided by x. So that's our formula for converting BPM into an interval for our counter. That brings us to the next task, which involves both hardware and software. First of all, build up the circuit that you see here on the breadboard. It involves a potentiometer, an LED, and a resistor, although we won't use the LED just yet. Once you've built up the circuit, then adapt the code from the previous example to use analog read to read the potentiometer. Then use the map function to scale that to be between the range of 40 and 208 beats per minute, which is the typical range of classic metronomes. From there, you'll need to convert the BPM into an interval in samples, then use that in the timing code. And here, for reference, is the same circuit on the Bela Mini. Pause the video here and try that. Let's look at the core of the code first. Here's our analog read function, which reads the input connected to the potentiometer. K input tempo will be declared at the top of the file. Notice that analog read reads frame n over 2. The reason for that is that the analog inputs have half the sample rate of the audio inputs by default on Bela. It's a good idea to have some code inside of setup to check that that's actually the case and potentially stop your program if the assumptions are violated. Once we've read the input, then we need to map it to the desired BPM range. Notice that I'm mapping 0 to 3.3 volts to the range 40 to 208 BPM. From there, I calculate the interval and samples according to the formula we saw earlier. Then the rest of the code looks largely the same as it did before. Alright, so here we have that code in context. We can run this project. And we can see that we're starting from a very slow tempo, which we'll now adjust with the potentiometer. All right. What we've looked at so far is how to generate discrete events at regular intervals in time. A related question is how to generate a signal that persists over a certain interval and then stops. For example, to make a pulse that lasts for 1/10 of a second. How do we do this? Well, the idea is the same as before. We're going to count audio samples until we reach a certain number representing 1/10 of a second. However, unlike before, instead of having something that happens only once when that count elapses, we're going to have something happen every single time through the loop until the count elapses, as shown in this brief bit of pseudocode. The way we're going to try that here is to add a blinking LED to our metronome. If we only turn the LED on for a single audio frame, the flash would be so brief we wouldn't even see it. So what we want to do is keep the LED on for, let's say, 50 milliseconds at the beginning of each tick. What we're going to need to do is count samples like we did before, and we'll use the digital write or digital write once function to set the LED to be on or off each time round. A hint for this code is that you can still get away with just one counter keeping track of how many samples have gone by. You just need to compare it now to two different intervals. One interval tells you whether you've reached the next tick, and the other interval tells you if enough time has elapsed that you should turn the LED off. Here again is the circuit for the Bela Mini. If you haven't yet put the LED onto your breadboard, do that now, remembering that the short lead of the LED should go towards ground. Pause the video here and try this. As before, we'll start with a condensed overview of the code. We'll declare some variables at the top of the file, including a constant that tells us which pin to use for the LED so that we don't have to remember the magic number down inside of our render code. Remember that we have to set that pin to be an output inside of setup if we want this to work properly. As before, we have the same two variables, gMetronomeCounter and gMetronomeInterval, and a new variable, gLEDInterval, which holds the number of samples for 50 milliseconds. Then inside of render, we're going to add an if statement to check if the counter is less than the LED interval. If it is, the LED will be turned on, otherwise it'll be turned off. Here's what this looks like in context. We have our constants telling us which pins to use, both for the analog input and for the LED. Then we have our counters and intervals that we looked at before. Inside of setup, we have the pin mode function, which is setting our LED pin to be equal to an output, and also calculating our LED interval to be equal to 50 milliseconds. Then inside of render, we have the code that we looked at a moment ago, where in addition to setting the interval based on the potentiometer, we are also checking whether our counter is less than the LED interval, and if that's the case, we set the LED pin to be high, which turns the LED on. I'm using digital write once here because I know that I'm going to be calling this every single time through the loop. If I didn't know that, then it would be safer, though slightly less efficient, to call digital write. Here's the rest of the code, and we can run that now. And there's our blinking LED. We can change the tempo as before. And there we go. So that's the metronome example. Before we finish this lecture, let's go back to the step sequencer that we first built in Lecture 7. The step sequencer is a fundamental building block of many forms of electronic music. It's essentially a way of playing a repeated pattern of events in a loop. We might use a step sequencer to store note values or drum events or other kinds of values. The idea is that every time the step sequencer gets a trigger, it advances to the next step. So, as before, we're going to focus on using this to control the pitch. The way we implemented this in Lecture 7 was with a series of values stored one after another in an array and a read pointer to tell us which value we're looking at right now. We saw before that this structure was very similar to what we needed for a wavetable oscillator, the main difference being that the read pointer only moved when we received a trigger and not every sample. Our step sequencer today will start very similarly to before, in that we'll have a buffer holding a series of frequencies, and we will move the read pointer when we receive a trigger, like this. Last time around, we used a button press to create that trigger, and we were looking specifically for transitions from button not pressed to button pressed in order to generate a trigger. We'll do it differently this time, essentially merging code with the metronome, so that when a certain number of samples elapses, then we generate the trigger to move on to the next step. The example code in the companion materials gives you most of the step sequencer. Your task is to implement the metronome part of it, to count samples as you did before, and to advance the sequence when the interval expires. Also include the code you just made to blink the LED and to change the interval. You might find for the step sequencer that you want to have higher BPMs available than just 208, so try 500 or even 1000 as a maximum value. And if you want to, of course, you can experiment with the MIDI note values inside the step sequence to try creating other patterns. This is the last example for today. Pause the video and try it. Okay, here we are. To start with, we have a number of global variables at the top. Some of these were used to implement the step sequencer itself, but we've also added some constants to keep track of the input and output pins, and then also these intervals that we've used in our previous metronome code. As before, we can go down into Setup and see that we are initializing the intervals inside of Setup to take account of the current audio sample rate, and that we're calling pin mode at the beginning to set the LED pin to an output. Don't forget to do that or the LED won't light up. Then we can go down to Render. At the top of the for loop, like before, we call analog read and then map and then eventually calculate the interval in samples. And then below that, we have some of the step sequencer code, which reads the current MIDI note out of the sequence buffer. The conversion from MIDI note to frequency is described in a previous lecture. This bit of the code implements two detuned oscillators to produce a richer sound, and this part of the code is new. Here, we're incrementing the metronome counter, and when we reach the interval, like before, we reset the counter to 0, but rather than triggering an audio file, this time we're going to advance the sequencer location. We check if the location got to the end of the sequence, and if it does, then we reset it back to 0 so that it always plays in a loop. Below that, we have our code for dealing with the LED, which is essentially the same as it was before, and then a lot of the code that was given to you, writing to the audio outputs, converting the MIDI note into a CV, writing that to the analog output, and then finally logging the result to the scope so that we can see it. So we can run this code now. And we can open the Bela oscilloscope. And we can see the oscillator output and the CV both are changing. Then we can also change the speed, as we did before. All right. A couple final caveats about this approach to measuring timing. Counting samples as a way of measuring time in seconds depends on a precisely known sample rate, and we don't always have that. Even when we do have reasonable precision for our sample rate, the system clock that gives us our wall time is not necessarily synchronized with the clock that's giving us our audio sample rate, and in fact they're often derived from separate physical oscillators inside the computer. There might be one oscillator responsible for the 1 Hz system clock, and another oscillator entirely which is divided down to give you the 44 kHz audio frame clock. Because these are physical bits of crystal with imperfections in manufacturing and variations in temperature, they can be expected to drift from one another. A typical amount of drift might be something like 20 parts per million, which is quite small, but it still works out to about a difference of 1 sample per second at 44 kHz. And over time, these divergences can add up. So if it's very important for your code that your timing also corresponds to the computer system clock, you might have to take other measures as well. That brings us to the end for this time. As always, click subscribe to be notified of all the new videos as they come out, or follow us on social media where we announce new developments in this series and in Bela generally. You can find useful resources at our forum, where we provide community support, at our blog, where we share projects made with Bela, and the knowledge base at learn.bela.io, which has a lot of tutorial materials. Thanks a lot for following along with this lecture. We'll see you the next time.